Hello YouTube and welcome. Today I want to talk a little bit about gravity. Two reasons for doing that. The first is that I've been doing some experiments or some tests to try to repeat the Cavendish type experiment just using some domestic items. Slice Barkane published a video of that sort fairly recently, and I published one soon after. And it became clear that what I was observing, and I suspect partially what Sly might have observed, was the effect of air currents on the apparatus rather than only gravity. And I've done lots of tests since, and I'll be publishing the results of those fairly soon. The bottom line is, if you take enough care to eliminate air currents and to repeat the experiment or the test often enough and carefully enough with the right kind of setup and apparatus, it's perfectly possible to reproduce the Cavendish experiment and confirm that objects do indeed attract each other. Objects, if they have sufficient mass. With less mass, the attraction is too small, the attractive force is too small, and any other effects of air movement and so on tend to interfere. Certainly in my hands, anyway. So the second reason for talking about gravity, though, is that this video on screen at the moment from Anthony Riley, aka Sleeping Warrior, shows or makes a number of obvious mistakes that flat earthers tend to make about gravity. And also, Anthony, actually, the example that he uses in an effort to show that there is no force of gravity, the example he uses actually shows that there most definitely is a force of gravity, really quite clearly. And so that's what I like to talk about. So the video, Riley's video, starts with this statement, "Show me that gravity." And indeed, later on in the video, Anthony, you do show the effect of gravity. Obviously, you can't you can't see gravity itself, but you can see its effect, as you do in the Cavendish experiment and as you do in the observation that you report here in this video. It's not your own observation, but it's an observation that you've found from somewhere. Anthony starts the video by talking about this article in Scientific American, and he particularly refers to the difference between Isaac Newton's original description of gravity and the more recent work 100 or so years ago of Albert Einstein and general relativity. And he makes the point that that Einstein's general relativity is kind of the best current explanation that we have, or description of gravity that we have, and therefore Anthony says that all arguments about whether there is a gravitational attraction or not between objects should be expressed in terms of Einstein's general relativity, and nobody should refer to Newton. Now, that's actually not true. Newton's equations and observations work perfectly well in situations where there's relatively little gravity. For example, like on the Earth. Although the Earth is a fairly massive object in comparison with ourselves, it's not very big in comparison with the gas giants of Jupiter and Saturn, and even less in comparison with the Sun. Newton's equations work perfectly well on the Earth and on smaller planets and so on. Newton's equations weren't observed to start being slightly inaccurate until the the orbit of Mercury could be carefully measured. Because Mercury is so close to the Sun and the gravitational attraction from the Sun is so huge, especially at that distance, it was found that Mercury's orbit did not quite match what Newton's equations predicted. And it wasn't until Einstein's general relativity came along that a better explanation that matched Mercury's orbit was possible. And it's true that Einstein's general relativity better explains the gravity that we observe. It predicted gravitational lensing, which is something that's been observed. It predicted gravitational waves, which have far more recently been detected. And so Einstein's description of gravity is considered to be much better. But we also know that Einstein's description of gravity actually breaks down in very, very extreme cases, like the center of a black hole. So even Einstein hasn't got a perfect answer. And this is one of the points about science. It's a process really of constant refining of our understanding of the universe, rather than there being kind of dramatic changes to our understanding. There will be occasions when there is a huge paradigm shift, but not very often. And it's possible that one day there'll be a massive paradigm shift and somebody will come along and explain the observation of gravity in a different way to the way that Einstein described it. But it may simply be that a kind of revision or improvement of Einstein's work will actually lead to the more full understanding of gravity. Anyway, that's not the point that I want to make today. The main point is that Anthony Riley presents this observation of an anvil being placed into a bath of mercury, and uses this as an example of how no force of gravity exists. And well, I'm going to play you a little bit of what Anthony says, and then discuss what he's saying. I may pause the video briefly to just make points as we go along.
5 grams per meter cubed. So back to the observation, I've put the two values in to reflect the liquid and the metal, and as you can see, you would be able to make.
So the two values that he's referring to are the densities of the anvil and the density of the mercury. I'm just going to back that up a bit so you can hear the next part that he actually says. So the anvil has a lower density than the mercury. It weighs less per cubic centimeter than the mercury does.
And as you can see, you would be able to make a prediction as to what the metal should do in this liquid.
So he says you should be able to make a prediction of what the metal should do in this liquid. Both the liquid and the anvil are in fact metal. It's a minor point, but the mercury is a metal, just a liquid metal. And yes, Anthony, you can make a prediction of what the anvil will do in this liquid. I notice that you don't actually make that prediction. In the case of gravity, if you know the mass of the anvil, you can calculate its gravitational attraction towards the Earth. And you also know the density of the mercury. And if you could calculate the rather strange shape of the anvil and measure the amount of mercury that is displaced, or if you had some mechanism by which the displaced mercury was siphoned off into a another container, and you could measure the volume that was displaced, you would be able to calculate the buoyant force for the actual amount of mercury that is displaced. And what you would discover is that the buoyant force would exactly match the gravitational force. And so the anvil will float once that particular amount of mercury is displaced. Your assertion in this video is that there is no downward gravitational force, and that the only thing that matters is the density of the two objects, the mercury in the bath and the anvil. But because the anvil has a lower density than the mercury, if the only thing that matters is density, then the prediction from your hypothesis would be that the anvil should rest on the surface of the mercury and not penetrate the mercury at all. If only density was important, that's what should happen. And that is not what happens. The anvil does enter the mercury and displace a significant amount of mercury. It appears to sink in about halfway and displace a significant amount of mercury. Now the video goes on and shows somebody pushing down on the anvil, so adding to extra force on top of the force of gravity, and then releasing the anvil, and it bounces back up. Once again, this is exactly what we would predict to happen if the forces of gravity and buoyancy are reaching equilibrium. But if density is the only thing that matters, the anvil should move back up under the effect of the buoyant force and rest on the surface of the mercury.
Liquid relative to its relative densities. And it's only when the hand pushes the anvil underneath the liquid do we see any evidence of a force. That's critical. You need the hand pushing down to demonstrate the force.
No, you don't need the hand pushing down to demonstrate the force. The force is demonstrated perfectly well by the fact that the anvil floats partly submerged in the mercury. This demonstrates that something is pressing it down that far. That is further confirmed by the fact that if a person pushes further or pushes down on top of the anvil in this position, it travels further into the mercury. It only travels into the mercury due to the force. And that force, Anthony, is called gravity. Now, later on in the video, Anthony presents another example which shows exactly the same thing. He's used this before in a debate that I had with him on my channel. The object at the top here, this spherical object, is resting on the lamp oil liquid, ping pong ball here. But it isn't sitting exactly on top with a single point of contact. It is partially submerged in the lamp oil. Again, this is due to gravity pushing the ping pong ball into the lamp oil, even though the lamp oil is more dense than the ping pong ball. And there are other examples further down. There is some a cherry tomato here in between the water, which is green, and dish soap, which is in yellow here. And it appears that the tomato is actually partially in the water. It hasn't fully entered the dish soap. Because the picture is taken at an angle, that may not be exactly what's happening, but that's how it appears to me. Further down here, you have a popcorn kernel, a dried corn kernel, And again, this is sitting halfway between two liquids of different density. The popcorn kernel is being pressed into the corn syrup, even though the corn syrup is a higher density than the popcorn kernel itself. So what is pushing the popcorn kernel into the corn syrup? What is pushing the cherry tomato into the dish soap, but leaving some of it is still in the water? And what is pushing the ping pong ball into the lamp oil? If density was the only factor at play, then these observations would not be possible. Another point that Anthony makes in the video made me laugh. I mean, I just laughed out loud when I heard him say this. He looks at the description of force, the definition of the word force, which is fair enough, but not a particularly scientific version. And then he goes on to talk about Newton's second law, force equals mass times acceleration. And let's hear what he has to say here.
Sure, in maths, a mathematical equation is force equals mass times acceleration.
Well, it's a physics formula in the form of a mathematical equation. But anyway, let's carry on.
But it requires a physical action. So if you haven't got the physical force, you've just got this.
So at this point, I couldn't help myself. I laughed hysterically. The equation, Anthony, is force equals mass times acceleration. If you have mass times acceleration, you have a force. And he goes on to say,
an accelerating mass. He
goes on to say, all you have is an accelerating mass. Well, if you have an accelerating mass in physics, according to Newton's second law, you have a force. Now, if you want to claim that you can have an accelerating mass and it does not equal force, then please be my guest and go ahead and produce some good empirical evidence, mathematical proof, or other means of demonstrating that assertion. But the fact is that force equals mass times acceleration. So if you have an accelerating mass, you have a force. And we call that force gravity. You can call it anything you like. Okay? I don't care what you call it. It's there. The anvil, being partly submerged in the mercury, shows that it is there. Furthermore, you can actually do, here's an experiment you could go and do, Anthony. Take an object that will float in a particular liquid. Don't care what the liquid is, and I don't particularly care what the object is. Find something that will float partially submerged. And then, if you can get an identical object to the first one, so that its mass is the same, place the second object carefully on top of the first object. Now, I've actually done this with some rubber blocks, but I didn't have a camera with me at the time. I just wanted to check things out. And what you find is, although the density of the object that you are using has not changed, adding a second piece of the same material does not alter the density of that material at all. Its density remains exactly the same. the object is pressed further into the liquid by the addition of a second piece of material. So for example here, if we placed a second anvil on top of this first anvil, the first anvil would be pushed further into the mercury. If density is the only factor, then that shouldn't happen. It shouldn't. If density is the only factor, it should rest on top of the mercury, and it should not matter how much material, how much mass or volume of material is placed on top. If the density remains less than the density of the mercury, it should not penetrate the mercury. But if gravity is the cause, if gravity exists, then it will penetrate the mercury or penetrate the liquid. So I've done this with 2 rubber blocks in water, and I can show that with this one block, the rubber penetrates the water by a certain amount, and when you place a second block on top, it just about doubles the amount of block that is below the surface of the water. Explain that purely in terms of density. Purely in terms of density, nothing else. I don't think you can. The only way you can explain it is to posit some kind of force acting on the rubber blocks in my experiment, or the anvil here. And that other force is gravity. So thank you, Anthony. You have demonstrated the existence of gravity very nicely for us, and I'll be presenting my Cavendish experiments that confirm confirm that objects of mass attract each other. Another demonstration that gravity is real, gravity does exist. Thanks for watching, and hopefully I'll see you all soon with a few more videos.